Hey everyone, have you ever really thought about what a computer sees when it looks at a photo? Because it's definitely not a picture, not in the way we think of it. It's a giant grid of numbers. And today, we're going to use Python to reach in, grab those numbers, and mess with them directly. You're about to become a digital artist, and your paintbrush, it's going to be code. Let's dive in.
So let's start with that one big question. When your computer processor looks at an image, what is it actually seeing? I'll give you a hint. It's not a flower, it's not a sunset, it's not a face. To the machine, it's just pure data, a really well-organized collection of numbers that we can measure, we can read, and, this is the best part, we can change.
Okay, so our very first step is to get this image out of its cozy little file and into a format that our code can actually play with. We are, essentially, unlocking the digital canvas to get to the raw paint underneath. First things first, we got to get our tools ready. We start by importing CV2. That's OpenCV, which is pretty much the gold standard for computer vision stuff. Next up, we grab matplotlib.pyplot. It's an awesome library for making charts, but for us, it's going to be our window to see our results. And then, the first real bit of action, cv2.imread. This single line of code reaches right onto your hard drive, grabs that image file, and pulls it into our program's memory.
And just like that, it's not a .png file anymore. The image has been transformed into something way more powerful, a special data structure called a numpy array. This right here is the magic moment. We've successfully translated a visual thing into pure, structured information that our code can now work with.
So, what in the world is a numpy array? Honestly, the best way to think about it is like a giant spreadsheet. But instead of financial data in the cells, each cell holds the color information for one single pixel. It's literally a digital canvas, built from nothing but numbers.
Now that we have this digital canvas, how big is it? Well, we can just ask it. We can ask for its dimensions or its dot shape, and when we do that, we get back three numbers, 32, 32, and 3. This is the blueprint of our image. So what do these numbers actually mean?
It's actually super straightforward. The first number, that's the image's height, 32 pixels tall. The second one is the width, also 32 pixels. And that last number, the 3, that's where things get really interesting. That 3 tells us that for every single one of those pixels, there are 3 separate numbers that define its color. You know what that means? This tiny little 32 by 32 image is actually made up of 32 times 32 times 3, which is over 3,000 individual numbers.
Right, so that number 3 is our ticket to understanding color. Each of those 3 values is a color channel. But, and this is a big but, here's a classic trap that a lot of people fall into. Different tools can speak slightly different color languages, and if we don't get the translation right, our image is going to look, well, really, really weird.
And here it is, the classic mix-up. OpenCV, the tool we use to load the image, thinks about colors in BGR order. That's blue, green, red. But Matplotlib, the tool we're using to show the image, expects them in RGB order, red, green, blue. So if we just hand the data over as is, all the colors will be scrambled. A red car would look blue, green grass might look purple. It's a mess. Luckily, OpenCV gives us a super elegant one-line solution. This function, cv2.cvcolor, is basically our universal translator. We just tell it, hey, take our image and convert the color from BGR to RGB. And boom, just like that, problem solved. Okay, deep breath. Our data is loaded, our colors are correct. Now the real fun starts. We can finally start messing with the image with absolute pixel-perfect control. It's time to start painting by numbers.
So how do we grab just one single pixel out of our whole grid? Well, it's just like coordinates on a map, or even a cell in a spreadsheet. You just specify the row, and then the column. Oh, and one important little detail. In the programming world, we always start counting from 0. So when we say IMG RGB 1718, we're actually getting the pixel from the 18th row down and the 9th column over.
But just reading data is only half the fun. We can also write data. This line of code is a direct command. We're pointing to the pixel at row 10, column 16, and we're totally overwriting its color. We're setting its new RGB values to 255, 255, 255. Since 255 is the brightest a color channel can be, setting red, green, and blue all to the max gives us pure, bright white.
This relationship is everything. The code is the action, and the change on the image is the result. We just changed 3 little numbers in our giant array, and in doing so, we turned 1 pixel on the screen bright white. This shows you the kind of total, precise control we have over every single point on this digital canvas.
Now, changing one pixel is cool, but it's not very efficient, is it? The real power of using these numpy arrays comes from applying broad strokes, making huge changes to the entire image all at once, sometimes with just a single line of code.
For example, what if we wanted to make the entire image darker? It is shockingly simple. This one line of code takes the entire array, all 3,000 plus color values for every single pixel, and divides every last one of them by 2. The result? Every color is now half as bright, and the whole image darkens instantly. That's the power of vectorized operations. We can even do more complex things like rearranging the pixels to create geometric effects. Let's say we want to transpose the image. That's kind of like flipping it along a diagonal line. We can't do that with simple math. We have to physically move the pixels. The process is pretty logical, though. First, you create a new, blank canvas. Then you'll loop through every single pixel of the original image. And here's the clever part. You copy the pixel from coordinate ij in the old image over to ji in the new one. Just by swapping those coordinates, we get the flip.
All right, we've loaded the image, we've fixed its colors, we've manipulated the raw data. There's only one thing left to do, the grand reveal. We need to turn all those numbers back into a picture that we can actually look at.
3 simple commands will bring all our hard work to life. First, plt.imshow takes our final numpy array, that transposed image we just made, and gets it ready to be displayed. Then, plt.axisOff. This is just a little cosmetic touch. It gets rid of the boring axes around the image for a cleaner look. And finally, the command we've been waiting for, plt.show. This is us telling the program, okay, you can put it on the screen now.
So let's just quickly recap that journey. We started with a static image file, right? We unlocked it, turned it into this dynamic grid of numbers, our digital canvas. Then we used code as our paintbrush to change that data. And finally, we render that data back into something visual. From file to data and back to a picture again. Pretty cool.
And all of this brings us to what I think is the most important takeaway. An image isn't just a picture. To a programmer, it's a landscape of data. It has height, it has width, and with color, it even has depth. It is a numerical world that you can step into, explore, and reshape in any way you can possibly imagine.
And look, we've really only scratched the surface today. We changed one pixel. We darkened a whole image with a single command. We rearranged every single pixel to flip the image. If this is what's possible with just a handful of very basic commands, imagine what else you could do. So the real question isn't just about what's possible, it's what will you create next.